From each corner of a square piece of sheet metal, you are going to remove a square of side 9 centimeters. Then you're going to turn, not of the edges, but up the edges to form an open box. If the box is to hold 144 cubic centimeters, what should be the dimensions of the piece of sheet metal? Okay, isn't that beautiful? All right. Wait, what? Okay, so what are we starting with in the problem? Not 9, not the first number you see. What are we starting with physically? Okay, a square piece of sheet metal that's getting turned into a box. So we have something like this that eventually is getting turned into, I know, something like this. Sorry, those of you that had Miss Hoffman, okay? Sorry. All right. I don't compare. I don't try that hard either, I guess. Okay.
It looks wonderful.
Oh, thank you. Thank you. I'm just going to refer back to my Miss Doll is amazing thing every time I mess up, and then I just feel fine about myself. Okay? All right. So we have a square piece of thing that's going to get turned into this little box. How are we turning it into a box? We are removing a square of side 9 centimeters, and that was from each corner. So what's happening is we're cutting squares off here. Here. Those are beautiful too. Okay, so we're going to cut these off. And then we're going to have something that we could fold into kind of like an open looking box, right? You would fold along this area right here. So visually, do we get what's happening in the problem? Okay? Now let's figure out what's going on. The only thing we really know is that these are all squares, what we're cutting out and what we're starting with. Okay, so they all have equal side lengths. Do we know the entire side length of this side? No, but that is what I'm supposed to figure out in the end, right? So if it's okay with you guys, I'm just going to call it right now X. Okay? And I'm not going to say this is the easiest way to do this problem. I'm going to do it this way because later on you have some other things. All right. Now, knowing that that whole distance is X, okay, and then looking at what we know numerically we know that these little squares that are getting cut out have side lengths of 9. So those are little 9 by 9 squares that we're cutting out. And we know that the volume of this box that we form is supposed to be 144 cubic centimeters. Oh, that's not too big. Okay. Is that all right? Okay. So this is where I can set something equal to something, right? Because I know something about volume of a box. How do I calculate volume of a box? Okay, so the length times the width times the height. So if I can figure out the length times the width times the height, I know that that's supposed to equal 144, okay? Then it comes down to, then what do I know about the length, width, and height of this box that I have formed, okay? So first let's talk about height. Anybody know anything about the height of the box? 9. Good. How does he know that? We cut out squares that were worth 9. Meaning this little edge right here is 9. So when we fold up the edges of the box, it's going to have that height of 9. Is that okay with everybody? All right. So I got that. Now, we started with a square piece of metal, which actually works in our favor as far as calculations because it's kind of less calculations to do because we don't have two different measurements. We have the same. So we started with a certain side length. Same, all sides, right? Then we cut the same thing out of each corner. So the bottom part of this box we're building is still a square, right? Because it started from a square and we cut the same thing off all the different edges, 9 centimeters every direction. So this guy in here is still going to be a square, so still equal distances. So I know that these two measurements here along the base, which would correspond with this stuff over here, are the same, but I don't know what they are, okay? Can I write an expression to show what they are in relationship to what I've already marked up here? Okay?
Since you already know what 9 is, you can just do 9 times the width times the 9 times the width squared.
Okay, good. Okay, so let me bring up what he's saying here, and then I'm going to talk about another way to do this just for when you're given different dimensions. So basically, you don't know what they are, but you know that they're the same, right? So if you want to call this the width, you could call this the length, or you could just call it the width again because they're going to be the same. Is that okay with everybody? So basically, he's saying those are the three things you would multiply together in the volume formula to get your 144 cubic centimeters, okay? All right, so then we'll go ahead and we'll divide by 9, right, on both sides. So this is 9w squared equals 144. And so we get w squared equals 16. Now, algebraically, when we square root the 16, we're getting plus and minus 4. But in this case, if this is supposed to represent the width of the box, like a physical thing that we've built, the negative 4 has no validity here, okay? So I always point that out because I don't want you to think I've like changed the rules. Like, oh, before she said when we took the square root, it's plus and minus, and she's breaking the rule. Like, no, there's context to this problem, and the negative 4 doesn't fit in the context, okay? So I get 4. So then I know that this is 4, and this is 4. So that means over here, these are 4. Okay? But my job was to find the dimensions of this square piece of sheet metal, okay? So what is the length of a side here? Not 17, 22, right? Because we have 9, 4. I drew it way not to scale, but I didn't know when it started, right? So 9, 4, and 9 would make up the entire length of the side. So 22. These squares out here? Yeah. You don't know what they did with them. Maybe they did something with them. Oh. Okay, so the dimensions are 22 by 22 because it's a square. Now, I want to go back to what I started at the beginning and just show you a different approach, because if this was a rectangle, this would not have been so nice right here. This was nice in the fact that even though we didn't have to use anything else from here, we could just come over here and call this whatever we wanted and solve for it, because it was two of the exact same thing being used in the equation. We just had to be able to take a square root here, right? If they had changed the problem so that it was a rectangular piece of sheet metal, first of all, we'd have to know something between the width and the length relationship, or else we couldn't write it all in terms of the same variable. Okay? Secondly, these numbers would be different then, right? And we would depend on their relationship with each other to write this, and it wouldn't be as simple as it is right here. Okay? So an example of how you can approach that, just for those of you that struggle with then applying it there. Let's say that we had a situation, same type of situation, except for let's say it was a rectangle, and they told you that this side, I don't know, was some length, and the other side was double it. I'm just making up my own problem to make it a little bit different, okay? Then when you cut the 9-inch squares out of the sides, yeah, those are beautiful looking. Okay. So you still are getting the same type of scenario where you're going to fold up this box, and because these are 9 inches, you know that the height of the box is going to be 9 inches. The difference is that when you build this box, even though you know that this is 9, okay, you can't just call these two the same thing anymore, right? Because they didn't start with the same idea. Okay? So just some ways to remind you of how you can express different things. If you don't know that they're the same, there still is a way for you to express them starting with edges of like x and 2x. We could say then that like this distance right here, it was x, and then it was cut 9 inches, or whatever they were, centimeters short here and 9 centimeters short here. So the length of this is going to be x minus 18. It's not as friendly of a way for me to express it, but still a way. So just a reminder from some of that geometry skills that you guys had before in setting up equations. And then here, this was 2x, okay? But it's being cut short 9 centimeters here and 9 centimeters here. So this length would be 2x minus 18. Okay? Even though they're not the same, if I can write them in a way where I can express them with the same variable, it's not going to be nearly as friendly to calculate. But I could still then set up some sort of equation to help me find the dimensions. Okay? Now, in this case, I'm not going to have to take a simple square root, right? There's probably going to be a lot more going on over here on this side. Okay. So how do you think I'm going to be able to solve for x now that I figured out an equation from the information? If I can't just take square root of both sides after I divide by 9. Okay? Okay, yeah. You can simplify it enough so that you can either factor or use the quadratic formula or completing the square. Some skill that you do already have, but you have to remember that you have it to help you get through the rest of the calculation. Okay? All right? So I showed you the square one because we could, once we broke the problem down, it was a little easier to see where it was coming from. But know that if the situation gets more complicated, we can still be okay as long as we can relate these two things together in some way. Okay? All right. Second one that we're going to look at is going to be number 4 on that handout. Okay. The area of the opening of a rectangular window is to be 143 square feet. If the length is to be 2 feet more than the width, what are the dimensions of the rectangle? So somebody help us set it up. Janae? Okay. So she said the length would be something like x plus 2 if the width is x. So she related the two things together, right? Because it said the length is 2 more than the width. The length is to be 2 feet more than the width, right? So the width is something, the length is something that's that plus 2. Okay? All right, so what can I do here to figure out these dimensions then? Molly? Okay. And then this is similar. We have a quadratic type setup here, right? So we want to set it up so we can use quadratic formula or factor. And this actually does factor. Does anybody know quickly what 143 factors us? Close. Yeah. Oh. 11 times 13. Do you guys know like the trick of the 11? Yes. How many people know? No? How many people don't know? I mean, okay. Oh, okay. I'll show you guys. You guys will like this. Okay. So notice, like, okay, so 11 times any other 2-digit number. The first digit stays the same. The last digit stays the same. And the middle digit is like the sum of the numbers between. So like 11 times 13. So 11 times 12 is going to be 132. Because the 12 would have 1 and 2. Okay, but it's not magic. Like, think about it. 13 times 11. Okay, so the way multiplication works, like the 1 is going to, 11 only has 1s in it. That's why there's like a trick, right? So 1 multiplies 3, what do you get? 3. That's not going to be added with anything in the second row, so that's why the last number is always going to match, right? Okay. And then 1 times 1 is going to be 1. And in the second row, 1 times 3 is going to be 3. So it's not weird that those digits got added together. They got added together because the ones are multiplied, right? And then the only digit here, 1 times this is going to give us, right? Is that okay? So it's like cool, but it's like there's a really mathematical reason why it works, okay? All right, so here when we solve this, we get negative 13 or 11, but again, this problem has context. So negative 13 is not how long any dimension of our window is going to be, okay? So we solved, and we have that x is 11. X was our width. So this was in feet. 11 feet wide and 13 feet long. Or a width of 11 feet and a length of 13 feet. But 13 is not coming from here, people. Okay? This 13 is coming from the fact that the length was the width plus 2. So once I knew the width was 11, I added 2. Don't make magic where magic isn't. Okay? Magic is right here because of the way that it works. You don't just grab onto like, oh, it must come from over there. Like, no. If it doesn't make sense, then don't believe it, okay, till it makes sense. All right? Are we good? So you're just going to see different problems like this. That's going to be the last word problem handout. So you have your systems word problem handout. We talked about some motion word problems. All of that you had seen before in Algebra 1. I'm not saying you were good at it or not, okay? Maybe we need the review, but we had seen it. These, maybe not so much. A lot of these books are straight out of a pre-calculus text that used to be used for pre-calc honors, okay? And they still start with the same type of section, so I'm just kind of selling this to you guys right now that I'm like justifying myself, okay? That I am preparing you for what you have to do next, and that I explicitly decided to do this after talking to her about where she starts, and I think it would help you if they start with application word problems, that we take a lot of the stuff we know and we go over some application word problems, and that you'll be better prepared when you go into that course, okay? All right? So this packet's 10 questions long. We just did 2 of them.